Today we are going to dive into a presentation titled Mapping the Black Box. We will be exploring a fascinating new framework called Knowledge-Aware Active Learning, or KA2L, and looking at how it can actually cut large language model fine-tuning costs entirely in half. Let's get started. To understand the solution, we first need to identify the problem, which we call the SFT Blind Spot. Currently, training an LLM on an entire domain wastes massive computational resources simply because we cannot see what the model already knows. Standard fine-tuning is indiscriminate. The result? Incremental learning gets completely drowned in noise, and 50% of your training budget is wasted teaching the model redundant information. You might be wondering, why not just use traditional active learning to pick the best data? The issue is what we call the generative AI mismatch. Applying legacy active learning algorithms, like Corset or Badge, to modern generative models causes two major breakdowns. First, there is compute overload. Calculating gradients is computationally prohibitive at the scale of billion-parameter LLMs. Second, there is a paradigm mismatch, because these legacy uncertainty and diversity metrics were built for classification, not generative tasks. This brings us to a paradigm shift in fine-tuning. If we look at brute force SFT, it has extreme compute costs and low data efficiency. Traditional active learning has prohibitive compute costs when applied here. However, our framework, KA2L, is generative native. By utilizing the model's hidden states rather than gradients, it keeps compute costs low. And by using semantic entropy as its selection metric, it achieves ultra-high data efficiency. To stop wasting compute, we must stop treating the LLM as a black box. We do this by defining the knowledge boundary. KA2L acts almost like a sonar, mapping the model's internal latent space to find the exact boundary between high-confidence knowns and epistemic uncertainty, or unknowns. The proxy we use to identify this unknown territory is semantic entropy. Let's look at what semantic entropy means in practice. It's essentially consistency versus chaos. When a model has mastered a concept, it exhibits low semantic entropy. For example, if you ask how many keys are on a standard keyboard, it reliably outputs 100 for every time. But when dealing with unknown information, the model hallucinates, showing high semantic entropy. Ask an untrained model who holds the record for most knockouts, and it might randomly output Ali, Foreman, or Marciano. An LLM's inability to stably generate a semantically consistent answer directly flags an unmastered concept. Now, let's look at how we operationalize this. The KA2L architecture is a closed-loop system designed to diagnose, extract, and target an LLM's knowledge gaps. It works in three distinct stages. First, we probe the latent space. Second, we decode and augment the unknowns. And third, we fine-tune with precision. Stage 1 operates as a hidden layer sonar. Instead of doing computationally draining uncertainty sampling, we perform deep diagnostics directly on the model's representations. It turns out that uncertainty signals are encoded deeply within high-level representations, such as layer 31 for Llama 3. This makes latent space probing incredibly high-speed and low-drag. Once our sonar finds an unknown region, we move to stage 2, reverse engineering the unknown. KA2L takes an abstract unknown vector and uses a T5-based latent space decoder to reverse engineer those hidden states back into natural language. This allows us to generate diverse new questions, like who holds the record for most knockouts, or which boxer has the highest number of career KOs? That all target the exact same knowledge gap. This brilliantly enriches the training data without requiring any manual annotation. The impact of this targeted approach is profound. By actively selecting only the data the model does not already know, KA2L completely matches the performance of a full, unfiltered 10K dataset using just 5K unknown samples. That means we get matched performance while slashing annotation and computational budgets in half. Furthermore, KA2L is outsmarting traditional active learning. When legacy methods are adapted for LLMs on the NQ-open dataset, they fail to separate signal from noise, performing barely better than random sampling with a Rugel score around 38.7. KA2L's semantic uncertainty approach isolates the exact high-value data required, pushing the score up significantly to 44.96. To visualize what KA2L sees, take a look at the epistemic topography. On one side, we have a dense cluster representing redundant, mastered knowledge. On the other side is the scattered frontier where hallucinations live. The distinct boundary between them is the high-efficiency zone where targeted fine-tuning actually happens. To conclude, we are moving from black box to diagnostic learning. The era of training LLMs blindly on massive, unstructured domains is ending. KA2L proves that by mapping a model's epistemic topography, diagnosing exactly what it knows and what it hallucinates, we can achieve superior domain mastery with surgical precision, using only half the compute. Thank you for watching.